So welcome to today's webinar in a series of Innovation Hub webinars that we conduct here at Ferroperm Piezoceramics. So while you have time to log on, I'll just introduce our Innovation Hub, and then I'll pass the microphone to our speaker of today. So the Innovation Hub series is free of charge. It's some online masterclasses on the subject of piezoelectricity. And before going into details of that, I'll just briefly present our company. So CTS is a global company based in the United States. You see our geographical distribution on the left. We are present both in North America, Europe, and Asia. And on the right here, you see distribution on our various markets. So the idea of our Innovation Hub is to have a link to the outside world, which is not strictly commercial. It's a way of promoting new ideas. And we have the possibility, as you see, of like customer ordered projects and pilot production, and even up to full-scale production within this model. But we also have some free services that you see on the bottom left, where we do, for example, modeling and characterization. And we also, at the very left, you can also see the concept that we are in now, where we have some webinars presenting some important subjects in the field of piezoelectricity. So this is the contact details for our Innovation Hub, the email address directly for this. So now turning to the program of today, here you see the full program of this spring's webinars. We have 4 webinars, and we have come to the 3rd one. And today we are pleased to welcome Professor Vincenzo Esposito from DTU Energy. We'll be talking about new lead-free electromechanical ceramics and emerging processing technologies. And we agreed that Vincenzo will do a short presentation of his department and of himself. So please, Vincenzo, the scene is yours.
Do you mind to share my screen?
Yes, I'll just. So I think I will stop sharing now.
Yeah.
So, and I think you can. And while you're preparing, I'll say that all questions are welcome, and the plan is to have time for some questions, like half an hour through the webinar, and then some questions in the end. But you can, as soon as you come up with a question, you can put them in the chat or in the Q&A, and I'll try to keep track of them while Vincenzo is speaking. But the plan is to divide the talk in 2 parts. Okay, Vincenzo, please.
Yes. Sorry, can you see my screen just to be sure?
Yes.
Okay, good. So first of all, I would like to thank a lot CTS Ferroperm and Erling for inviting me to give this seminar online, and of course also I would like to thank all the audience, even though I cannot see them. I've been asked to report to some of our progress at DTU Energy about lead-free technologies for electromechanical conversion. And I thought that I would divide this presentation in 2 parts. The first part is going to be more on material science. The second part is going to be more on application and possible perspective on the processing new electromechanical active materials. This is also because I believe that innovation is not only on the scientific side or only on the processing side. I think it's a combination of the 2 factors. I hope at the end of this seminar I will convince you that there is a little bit of truth in what I'm saying. So I would like to start with my background. Despite I work in Denmark, I'm not Danish. I actually am Italian. I've been wandering around a little bit to prepare myself to this job. I come from the University of Padua, and I've been working for a long time at the University of Rome. And I had also some experience at the international level, both in the United States and South America, and also a few short experience in other countries. But I've been basically permanent in Denmark since 2008, and first as a scientist at the Regional National Lab, and now as a full professor at the DTU Technical University of Denmark. And my background is about ceramics. This fits well the mission of our department that deals with energy technologies that involves functional materials. I'm actually part of a subdivision called functional oxides, where we use metal oxides for different kinds of applications. You see here a few of them. And my background actually comes from ionic conductors, where we use metal oxides for fuel cells, electrolysis, sensors, and most of them work at high temperatures. So this is a kind of unusual presence for me in this piezoelectric environment. But in a minute, I will explain why it's not that strange. This is especially related to the first part of my presentation, which is about a new class of electromechanical active material that are oxygen-defective oxides. In this part, I will show you how these materials that have been used for many years as ionic conductors have actually very interesting electromechanical properties at room temperature. In the second part, I will give you a little bit of seminar work that we have been conducting in the last years to make some new electromechanical systems in the macro scale. And especially our focus is on additive manufacturing of ferroelectrics and piezoelectrics more in general. So let's start with the first part, which is about oxygen-defective metal oxides. These materials are metal oxides, so ceramics, and they are centrosymmetric. So first of all, we break the first law of the piezoelectricity. So we don't expect to have any electromechanical or very small electromechanical activity out of this. But they have a very special feature. They are missing of some of the very important constitutive part, which is the oxygen part. So somehow, if you think as a material as a structure that has several structural components, we are missing one of the pillars locally, of course, and this is creating in the material some kind of effects that can activate and trigger electromechanical response. This has been shown not by us, but some time ago already in 2012 by Professor Lubomirski from the Weizmann Institute of Science. And he has demonstrated this principle in cerium oxide, which is one of the defective materials with a fluorite symmetry, and where in a thin film shape under a pretty low electrical signal, you can actually have some actuation, very important actuation, actually pretty large. So again, we knew these materials for oxygen as oxygen ion conductors, and this is where they have been applied for sensors and fuel cells and electrolysis at high temperature. This is because those defects at high temperature are actually mobile, and they can we can transport oxygen vacancies through the structure just applying an electric field. And this is what you see on the right is a typical Arrhenius plot of at high temperature. We are talking about 500, 600 degrees C for these materials. They lack an oxygen, and the oxygen is basically the charge carrier. If you look a little closer at the structural level, you will see that the oxygen ion transport occur because there is some exchange in the site position of the oxygen vacancies. And this can happen through different paths, a different activation energy. But the most important condition is that we have enough thermal energy to activate this process. So together with the application of electric field, we can move these vacancies or if you look at from the other side, we can move oxygen from its position to the vacancy place. So we have this transport effect at high temperature. And of course, this transport effects depends on many things. And one of the important parameters that we are considering is the local distortion. For example, which is due to the dopants that we are using in the material. The dopants here are usually elements that have a lower valency, so they actually can induce formation of vacancies, but at the same time, they induce some electrostatic distortion of the lattice. And this can change the ionic conductivity. So if we want to go back to our metal oxides, defective metal oxides, as electromechanical functional materials, we will see that they have a response which is typical of the electrostrictors. And here I want to open a very tiny parenthesis on what is electrostriction. Electrostriction is a common phenomenon for all the insulating materials that under an electric field basically give a separation of charges. This separation, of course, leads to actuation or change of shape or strain in the lattice. So we have here already a difference between electrostriction in centrosymmetric material and electrostriction in piezoelectrics. In this case, it is just actuation. So we give an electrical signal, and what we get out in the material is a strain. We cannot, unfortunately, get the other function typical of the piezoelectrics, so the direct piezoelectric properties, where we, applying a strain, we get some electrical current. However, the electrostriction itself is pretty large. Another difference with piezoelectricity is that electrostriction goes with the quadratic law. That means that it has followed this parabola, and the signal is always positive, exactly because it's a quadratic law. And there are some, of course, there are some equations that describe this effect. These are schematically represented in this slide. So, electrostrictors are very interesting materials, electromechanical active materials, because they give a very nice, precise actuation. They don't depole, they have nice features, and they can stand to very high electric fields, usually. But in general terms, their properties are strictly dependent on the dielectric properties. And this has been studied a few years ago by Newman, who formulated an empirical law that says that the electrostriction coefficient is linear to the inverse of the electric properties along this line that you see in this plot. We can define such materials, commonly known materials, classic electrostrictor, because they follow this law. Well, when we go for the defective oxides, the very first thing we notice is that our materials are outside this empirical law. So the electric properties and mechanical properties are not strictly related. And why this is happening? It's actually very complicated matter. I will try to give you a few hints of what is happening at the material level. But just let's try to recap what is happening, for example, for cerium oxide, which is already in this plot. We have a fluoride structure with the oxygen vacancy. So our crystal is not perfect. It is missing an important component. And if we have a strong electric field at high temperature, we usually move this defect. But now we cannot move it because we are in room temperature condition. There is no thermal energy enough to do this job. And the result is that when we apply an electric field, the material starts to strain. And the strain goes back depending on the intensity of the electric field. What is also nice of this material is that this works in any possible ceramic configuration. So we go from a polycrystalline to single oriented films, polycrystalline films. We still find this effect. And this is, I think, pretty important because piezoelectric and only ferroelectrics have these properties after poling, right? And in ceramics, it is pretty rare and precious property. So the first question that we have when it comes to a polycrystalline system, which is a bulk ceramic material, is what is the effect of the disorder, so the grain boundary or the grain size. And we've been analyzing the electromechanical properties for several years. And we saw that you can see in these plots that the grain boundary, the grain size actually is affecting the electromechanical response, but especially at low frequency. So if you see here in these plots that we have this linear relation between the square root of electric field and the strain, which is typical of electrostrictor, there are also some not completely explained saturation effects. But what is actually important to notice here is that the electromechanical response change as a function of the frequency. So first thing is that depending on the configuration of the vacancy, we actually can modulate the electromechanical response. So we were trying to understand this effect, not only in terms of grain boundary, but also more in general in terms of electrostatic distortion of the lattice, for example, using a different dopants. And the starting point was to use a dopant or a combination of dopants that do not lead to any distortion to the lattice. And we have noticed that this configuration is the best in terms of electromechanical response, especially at low frequencies. On the other hand, when we start changing the size and the valence of these dopants, we change also the electromechanical response at different frequencies. And here we have a paper from Weissman, from Lubomirsky, that show this dependence. And interesting, we can also discriminate between two possible different mechanisms at low frequency and at higher frequency. And here at high frequency, I mean around 110 kilohertz max, because whatever we have above that value, it is extremely low. So we actually lose the properties above 10 or around 110 kilohertz. So since there are many possible different dopants and many possible different combination of dopants, we need to do some simulations of the DFT model. So we have to take the atomistic picture of these materials and start putting artificially and numerically different cations in the cerium oxide lattice. And this is actually interesting because it gives us a hint of what can happen. For example, if instead of using a 3+ acceptor dopant, we use a 2+ acceptor dopant. And what we recently discovered is that, for example, calcium and magnesium and strontium, they suppress completely the low frequency response. So this is also very important indication for us of how these materials are working. So that, on the other hand, it's also possible to manipulate the response, to have a material that has maybe a steady response on in a different range of frequencies. Other important options are using isovalent dopants that can be tuned depending on the processing technology that you are using. And this is the case, for example, of praseodymium doped ceria, which is actually a pretty good electronic conductor at high temperature. It's not that good at low temperature, but we see that when we use reducing conditions, so when we have a large population of 3+ praseodymium, we can get a very high electrostriction in a wide range of frequencies. And this is also very nice. So far, I've been discussing just about experimental results. It's a phenomenological approach. Where I can also extend this to the thin film part, because thin films are extremely important, especially when we go to miniaturization and especially the position on silicon and other substrates for the microelectronics. Because the current state of the art is based on piezoelectric and ferroelectric materials that sometimes are very difficult to be processed. While our cerium oxide, our oxygen-defective oxide, is straightforward. I have an example here where using some ceramic electrodes, for example, titanium nitride, we can have a direct deposition of a material that gets very stable. And the stability of the ceramic electrode is actually pretty important, and even superior to other metal electrodes that can be used in this technology. This is, for example, this paper, we show that gold is less mechanically stable than titanium nitride and get pretty interesting properties. Something else is the deposition at low temperature, because the crystallinity is now becomes not that important. I don't know if you remember this first part about the grain size. We can still keep electrostriction even though we have small grains. And so using low deposition temperature, for example, on glass, we can have a nice electrostrictor, and this is demonstrated here with a cantilever that can resonate at different frequencies. And what is nice of this part of the work is that the resonant frequency actually are confirmed and by console simulation. So this again all phenomenological, talking about experiments and results, but there are also some other considerations that we can do more at the theoretical level if we downscale our system to the nanoscale. And I think things gets very interesting here. However, we still need to produce some samples, and to do that, we go away from a classic processing technology for PVD or CVD, and we go for still PVD technology that would allow, though, to control with great precision the crystal, the composition of the crystal, especially the orientation of the crystal. We do that through, we are specialized here in using pulsar laser deposition for 14 films. And this allows us to create a very nice interface between substrates, which are single crystal. In this case, for example, we have a neodymium gallate oxide single crystal with the cerium oxide deposition. What is nice in this case is that we have basically a single crystal deposition on a single crystal substrate, which has no electromechanical activity whatsoever. And when we tune the deposition using different crystals with different orientations and different lattice parameters, we can actually get in a field where we can even control the lattice strain at the nanometric level. So we are basically taking our fluoride structure in a strain condition, which is imposed by the substrate. And this is what I will show you in a minute when we deposit the CGO on different substrate, like, for example, lanthanum aluminate or neodymium gallate or strontium titanate. They have a different lattice parameter, and the crystal grow with a different tension, with different strain at the lattice level. This is not only a possibility. The other possibility is actually to change the orientation of the substrate and get a fully relaxed system, and now explore what is the best possible orientation for the electrostriction effect in CGO. And for example, in this study, we discovered that the 0-1 orientation is slightly beneficial for the electrostriction effect in these materials. But going back to the strain, of course, we can make a direct comparison between what happens in completely strained films and in relaxed films. And this can be done pretty easily, just tuning the thickness of the film. So when we do thin films that are below 10 nanometers, there is a pretty high strain coming from the substrate. It's not uniform, but we can be averaged more or less uniform in the whole thickness. However, when we go to thicker film, the effect of the substrate, so the interface between the film and the substrate, diminish. And this is, at the end, we get basically a fully relaxed system. So if we compare, for example, 3 films on 3 different substrates, which are thin and thick, we immediately see that the lattice and the thin film will change shape because of the influence of the substrate. And now we can actually tune the strain to be either compressive, tensile, or we can even choose a substrate which even no strain at all. On the other hand, when we go for thick film, these are supposedly completely relaxed, and this is also what we see from our XRD, from our diffraction characterization. So let's go to the results of this case, and what we notice is that if we do a cantilever like that, we get the second harmonic, which is typical of the electrostriction. And then immediately we notice that the thick film and the thin film have similar properties when they are relaxed or in a tensile strain. We're talking about in-plane tensile strain. However, in the case we have a in-plane compressive strain, the electromechanical response is much higher. And we have done these experiments a few times, and we have also included other substrates, and the compressive strain is confirmed to give a much higher electrostriction in this cantilever configuration. And when it's basically gaining at least one or two orders of magnitude with respect to the polycrystalline system. And this is extremely impressive. So the conclusion for this is that the in-plane compressive strain favors the electrostriction effect. So since we like this kind of approach, because now not only giving interesting experimental results, but also defining some new possible mechanism in this material, we have decided to extend the effect of strain in a so-called multi-layer heterostructure. So in this case, what we do, we replicate the number of interfaces that we have between the substrate and the film in the film itself, using different materials that have a slightly different lattice parameter. And when we stack them together in a multi-layer system, we basically generate a compressive and a uniform, rather uniform stress in the material that gives a strain to the film. And this is confirmed, of course, through XRD. And this is the kind of compressive strain that we get in the autoplane for this heterostructure, which is made of a bismuth oxide, another oxygen-defective fluoride, and gadolinium dopesiria. So our study case electrostructure. Well, these materials are extremely, this configuration is extremely interesting. And what we notice immediately is that depending on the number of interfaces that we are putting in the system, we can increase electrostriction in orders of magnitude. So in this plot, you see our pristine CGO, film, and this is the heterostructure. And you see that this is going with a volcano type of behavior, reaching a maximum and then declining. And this decline is actually due to the limit of this technology that does not allow to go for too many interfaces, since they get very thin. They are around 1 nanometer. Then we start having some intermixing of elements. And this was also confirmed by chemical analysis, where we see that there is not much difference between the chemistry of one layer and another when we have too many interfaces, and the films get too thin. So this picture gives you an idea how many orders of magnitude and the electrostriction coefficient we can get using this strategy. And but I think what is interesting to notice here is that then the electrostriction that we get in this material is much higher than anything ever measured in this among ceramic materials, not only ceramics actually. You can maybe recognize here a few polymers and relaxo ferroelectrics, and even new materials that have been tested electromechanically just recently. These results, of course, are very interesting, and that actually since are so important, we could publish them on Nature. But the question remains: what is the mechanism here? And the mechanism is complicated, and we have been trying to disclose it using single crystals and doing a DFT calculation and the X-rays absorption at synchrotrons and various synchrotrons around Europe. And everything seems to be related to the fact that we have a local distortion around the oxygen vacancy in the structure. And this is thankfully going along with some models that exist already around the oxygen-defective fluorides, especially CGO and cerium oxide, where the different, when we basically see that around the oxygen vacancy, we can create both elastic dipole. This is basically a distortion, local distortion in the solid solution, and easy polarizability of the material. So when we apply an electric field, the charges around the effect can change direction and drag around the elastic dipole. We don't have time to go through this. I'm open to answer to questions about this topic, but this is more or less the dominant model that we have in mind right now. And this seems to also to confirm some of our results, especially those related to strain. And the DFT calculation tends to agree with this hypothesis. So, but a take-home message is also that as soon as we can get high distortion in the system, we can actually get a nice electromechanical response. And this has been done in another publication on science in collaboration with the PFL group, where we show that if we can strain the material applying a DC signal and overlapping an AC signal out of it, we can get actually some kind of linear response as typical of a piezoelectric material. This is nothing new. This is known that if you have a DC on a centrosymmetric system, you can actually get a linear response. This has been already formalized. But what is nice to see is that we can actually apply this effect, and it is pretty large, especially at low frequency. So with this, I conclude the part that oxygen-defective metal oxides have electromechanical properties that are ubiquitous. We find it in polycrystalline, in a single crystal, in the columnar structure, and basically at any scale. And the nice part is that there is still room for manipulation and improvement. And we hope to see these materials in action in real life very soon. I have concluded my first part, so if you have questions, please let me know.
Thank you very much, Vincenzo. Maybe while the audience is thinking of their questions, I can ask just one. I was thinking to begin with, these materials are generally coming from the field of ionic conductors. So how does it look in terms of electric conduction? I mean, electronic conduction. Is that an issue, or are they really good insulators in terms of electronic conduction? Can you say something general about that?
Yes, I can say in general about that. The materials we are analyzing are usually pure ionic conductors, especially in oxygen, in high oxygen content. Electronic conductivity in these materials, it is a possibility. It can arise in reducing conditions at high temperatures. So while in oxygen at high temperature, they are in the presence of oxygen at high temperature, they are pure ionic conductors. In reducing condition, they can become mixed ionic and electronic conductors. But this is again for high temperature application, where the thermodynamics are completely different. And there is a pretty dynamic exchange of oxygen gas with the ceramic itself. What we are seeing here is completely still, because we are at room temperature, where the thermal energy is very, very low, and the mobility of the vacancies also is very low. As the same we can say for the other electronic defects that we usually see in these materials at high temperature. Said so, I have to say that defects usually bring defects. So if you have an oxygen vacancy, it is possible to generate other electronic defects, especially if you apply pretty high electric fields. So they can be some electronically, but this seems not to harm too much the electromechanical properties, and somehow can even help in some cases.
Okay, thank you very much. Actually, there are two questions. So maybe we have time for both. So the first one is, can you use the electrostrictive material for energy harvesting?
The answer is no, because the electrostrictors are basically only actuating. So if you want to talk in terms of piezoelectricity, what we get here is then the converse or inverse piezoelectric effect. It means that if you apply an electric field, you change the shape of the material. To do energy harvesting, you need the other effect. So you want to harvest the mechanical energy from mechanical waves or from a movement. You need to stimulate and strain your material to get electrical signal. So the answer is no, unfortunately. But on the other hand, we can do motors or other actuators and other kind of application.
Yeah, good. Last question for now is if we replace a small cation on a big cation in a cluster, what will be the effect on electromechanical property?
That's a very good question, and I have a partial answer for that. We have seen that if you go close to the solubility limit with your cations, so if you strain a lot your system in terms of electrostatic effects of the cation on the vacancy, we basically suppress the low frequency response, but we get a steady response in the high frequency.
Okay.
And this is probably related to the fact that these vacancy have a very low mobility, and they can even cluster in certain situations, in certain conditions. But they also require pretty high electric field, so the electrostation goes also a little down.
Okay, thank you very much. So I think with this little break, we will continue with part 2.
Yes. Actually, I'm very glad. This is a little bit more relaxing for me because there is a much less scientific topic in the conventional terms, and there is less materials and structures. Let's say it's more like application-wise. I like this topic very much. I've been trying to drag this into the framework of DQ Energy for some time, together with other colleagues, of course, not by myself. And I want to show you a few things that are related to the manufacturing of these of materials in general, of ceramics, let's say, in general, not necessarily electrostrictor, but also piezoceramics and the ferroelectrics. So, of course, when you talk about additive manufacturing, there are many different technologies that we can use. And today, we are covering some of them, but today I'm especially talking about stereolithography base. So we are basically digital light technologies. And I am specifically, even in this niche, there are different technical solutions to use light to process materials. But what is common for all these technologies that we basically exploit the lithography principle. So we have photopolymers that when they are irradiated with light, with certain lights, they polymerize. And we can drive the light in many different ways. There are some examples here in this slide, but it is important that we have a photopolymer system that can solidify under the light. And we have several examples. And here in this department, we are using this printer, which basically has an array of LEDs that can impress from the bottom above of photopolymer together with ceramic powders. So in this case, we call this as slurries. We put them in a vat that is impressed by the light, and can build up small shapes with a very high precision. What you get out from this printer are composite materials. So we have the polymer, photoimpressed polymer, solidified, together with the ceramic powders. So this is our green material that undergoes to the binding and sintering and gets into the sinter shape. This technique is extremely versatile and allow to print many different kinds of polymers, of ceramics. Okay, but we need to start from polymers plus ceramics. Another option that we have been exploring in collaboration with a Danish company called Addifab is to use the precision and the nice resolution of the polymer printing to make molds. So what we do is basically we do the template of the material, as you see in this video, and then we use a conventional feedstock material, which is a thermoplastic material together with a ceramic material, and we make a conventional injection molding. When I say conventional injection molding, I mean that we use the injection molding principle, but we are using a spatial mold. This mold is done by 3D printing, and this allows us to produce some shapes. You can see in this video that we have injected the material, And now this is the magic of this technology that is owned by the Adifab. We can dissolve the mold and get back the green that is ready to be debinded and sintered. So this technology, it's apparently simple, but has a very wide range of freedom when it comes to shapes. And we can print many different materials using just, let's say, conventional feedstocks. There are commercial feedstocks basically everywhere with different ceramics. And we can start getting some freedom in terms of shapes as well. And something else is also that when we sinter, we have a change of shape, which is not strictly related to the layer-to-layer deposition, which we have with other processing methods for ceramics, where we directly manufacture the ceramics. This is giving a nice example how the distortion can be controlled easily. And not only that, we actually can use whatever we know about injection molding to optimize our printing. And again, the flow in the mold can be controlled, and we don't have the layer-to-layer deposition or even the drop-to-drop deposition we have usually with other printing technologies. So I give you, for example, this is the barium titanate printing, where we show that just changing a few details in our mold can prevent the formation of cracks and other defects that are generated during the sintering, for example, where the stress can get so high and break the material. The finiture of the pieces is decent and can be of course improved. We have some example, but at the end what we get is always a nice and dense piece. And we have printed, we have started with the commercial feedstock, so we have developed feedstock by ourselves and printed several shapes. And the shape, what to print, is actually one of the questions that arise when you start doing additive manufacturing. And the first thing to do that we did is actually, cylindrical pellets, and that is actually to test the properties of our material. But of course, now we have maybe the freedom to change slightly the shape and make some lens or some domes that are anyways part of the current technology. So if you want, for example, to focus electromechanical waves, for hydrophones or acoustic lens, you need to have such curved shapes. But what to print is actually a burning question here, because if we want to introduce additive manufacturing, of course we have to consider what is the state of the art, where the processing steps are well established in decades and decades of production. There are still some few things that are complicated to be done with no mass production systems. Hydrophones are an examples, but there are also some other possibilities. But we, as innovators, we don't care about this, to be completely honest. I think if we have a very powerful tool like this, we should go for new design. And my personal opinion is that this electromechanical application field has been constrained by the shape for a long time. So, as a scientist, my first interest was to look in metamaterials. And metamaterials are materials that have properties that arise from the geometry and they go beyond the materials that decompose the material itself. And this is, of course, very well known for mechanical systems, for optical systems, but somehow these systems are, let's say, passive. They don't have intrinsic properties. We start seeing a few change in the literature when it comes to metamaterials with the active components, especially with piezoelectrics, especially when it comes to harvesting, energy harvesting, or composite. This Nature Material paper is an example of polymers loaded with some piezoelectric powders that can be used for energy harvesting. And we have tried that. We have tried that to do super lattices with our free injection molding, and this is one of the results. But the awful truth is that when you want to test these materials, for example, for electromechanical, for actuation, where you want to see what happens when you apply electric fields, you are in this very uncomfortable position to know where you don't know where to put electrodes and which kind of electric field to apply, because they are so resistive that is really impossible to go through that. So if you have an electrode-free application in mind, these lattices are interesting. If you don't have this option, it gets a little bit complicated to place electrodes in the right place.
You mentioned two main technologies of additive manufacturing. So there's the like the digital light projection and this other one with the freeform injection molding. Could you say something about the geometrical and let's say, geometry limitations and advantages and disadvantages with the two techniques?
Yes, of course. If you ask me about the difference between these two techniques, I think they are pretty complementary, let's say. When we go for the lithographic impression of slurries, including ceramic particles, that is a beautiful, amazing technology that allows to go to very high resolution, where high quality of the pieces. They are, if you are looking for individual complex geometries, this is probably the best possible way to go. And these are also where we have the nicer features in terms of resolution. We are ranging, it's a little bit difficult to say because each producer claims different values, but we are in the 10th of microns resolution when it comes to the digital part. And then the actual, there is also some a z-axis depending on the in-plane part that depends more specifically on the features of and the rheology of the slurries. So that also is in the microns, 100 microns range, 10 microns range. But what is nice of this technique is really the quality of the sample, and it's complicated though because it's you have to balance between the optical properties of the polymer and the conflictual optical properties of the ceramic powders, especially when it comes to white powders and black powders. They can have a different absorption of light, so it's complicated. What is also nice of this technology that can go multi-material. So you saw that we have this double bath system here that you can produce layer by layer different materials with different composition, because you use different baths. So we go for composition A, then we print on composition B, and then we build layer by layer the multi-materials. There are other technology also based on stereolithography that can go through multi-material in the 3 dimensions. So this is more or less limited to the 2D because we have to build up layer by layer, but other technology can also go with a certain complexity and an easier complexity in the 3 dimensions. So what I mean is that the 2 materials here are built layer by layer. So you have to go with many steps. Others can go a little faster. When it comes to the hybrid technology, I think this is extremely powerful, especially if you consider that you want to have a production that is faster and based on easy processable materials. Feedstocks are well known, are based on thermoplastics, and I think there is a big potential in this field. And when it comes to the resolution, I think it's a nice hybridization here, because you can have also nice features and details when you impress your mold. So now you transfer your geometrical features from the piece itself to its mold. So there are, I think, interesting application also in this case. The printer we are using right now is the one that we're using for as a pilot and has a certain limitation in terms of resolution. I gave you a few examples here, but there are printers that can go much better. They can do much better with the polymeric mold, and they get much better refinement. And I think this is part of the strategy of the Addifab to be. I think they have already in line this kind of technologies.
Yeah, thank you very much. We have a handful of questions, so The first one is about the let's say, commercial outlook. Do you think that 3D printing will be suitable for large-scale production, considering the complexity of the post-processing, like binder burnout and electrode printing and so on?
Well, I think that especially when you look at the hybrid technology, injection molding, there won't be much difference in what I'm not an expert in terms of the commercialization. I'm not the right person to answer to this question. But from outside, I can say that I don't think there are different issues than processing that you have with tape casting or extrusion ceramics. You know, it's still you are in the field of composites, where you have to burn out the polymers and control the shape after sintering. So I don't think on that side, I don't see big differences. And I think if injection molding is a good example where you can actually get into the mainstream of the ceramic processing. Maybe it cannot cover everything. There are other technologies more suitable for finer pieces with high resolution, like the other technology, the lithos technology, or I don't know, the DCRAM technology. But there is a good complementary field here.
Yeah.
And especially if you want to kind of have each piece be different from the other, it has to be, let's say, personalized for specific applications, then I think it's good to have a fast prototyping methodology. So it depends on what you want to do.
Yeah. Very good. So next question is, sorry, maybe I missed this, but do you pole the gyroid, and what material is the mold made of? And maybe I can add a third one. Can you say something about how do you put A and B electrodes without shorting them? So 3 parts about the gyroid. Yeah.
Yes. Okay. The polling, it's straightforward in case of the gyroid. It's basically we pole it exactly how you would pole a pellet. I mean, you have 2 electrodes. The only difference between having a pellet is the pellet have 2 parallel electrodes. Here they are simply, you know, very articulated, but still what you have in between, it's going to be poled, right? In the one direction. When it comes to these other guys, this is completely different story. The polling is a very complicated process. It requires too high electric field. You need to go for other technologies that are not disclosed. The other question was about
Yeah, there was a question about the mold for free-form injection molding. What material?
This is a proprietary technology of Addifab. They use a polymer that can be dissolved in a special mixture, and they will leave your piece free from the mold. So this is an example, but in other cases you don't need even to remove the mold, because maybe you can simply open it. For example, for the lens, we can open the mold without dissolving it. But for more complicated shapes, this is the case of this lens. I think I have it here. No, I don't have it. I'm sorry about that. But the lens can be basically the mold in two shells. You open it, you remove the piece. When you have a complex double helix like this, or the super lattices, you need to dissolve dissolve the molds in the process, like in this video that I'm showing again. And that's, of course, it's a polymer, photo impressive dissolvable polymer.
Yeah. Okay, I think let's just jump to the next question. I'll start with the second part. He's saying thank you for a very nice presentation. But then the question is, besides being beautiful, what is the purpose of these complex structures? Or the other way around, can you formulate a shape for a required function?
I'm not sure I understood the question. You say it is a beautiful shape, but what is the function?
Yeah, exactly. So what is the purpose of this very beautiful and complex structure?
Yeah, I'm not sure I am in the position to say what is the purpose. I mean, for some of these shapes, they are for focusing mechanical waves and so on and so forth. When you go to the gyroids, if you are specific, these are no purpose when it comes to piezoelectrics, for example. This is just a showcase. But when it comes to the gyroids, I hope I showed you today that we can have some kind of a mechanical amplification or amplification of the mechanical effect on large volumes as we usually do with multi-layer systems. So this is the slide that I refer to. So what I'm showing here is that with a constant voltage of 1 volt, in this pellet, I get a very low actuation, while in this large volume of piezoelectrics, I can get a pretty large actuation with the low voltage. And this is not different to what people have been doing with the amplification of actuation in the multi-layer stacks. So to reformulate, we know that ferroelectrics and piezoelectric have a tiny actuation, and often we need to amplify this without forcing the system to go to unbelievable electric fields. So what we do, we put things together. We even couple the piezoelectric materials with the mechanical springs and the cymbals and other things that can amplify the strain. What I'm showing here is that our gyroids can do the job without external components. So let's say that we can use this as an actuator, for example, to actuate a motor or whatever. So this is the suggestion that I'm giving today.
Yeah, and maybe just briefly, the last part is, are you actually able to formulate a shape for a required function? Maybe difficult question, but
I think it is possible, and it depends also on the application you have in mind. I'm not in a position to say too much about this, but I think this is a good example that I think it's a first step towards something different that we can do with these materials. Just consider that now we are actuating in a way that does not depend on the material, but depends on the shape. And then you can export this concept to new scenarios where you create maybe a different field of mechanical waves. Just to give an example, or that you actuate something that needs to be needs to go with large volume with low voltages. This, I think, there is room for implementation. Let's say.
Yeah. Okay. Thank you very much, Vincenzo, for this. I think the time is running, and some people had probably set aside just 1 hour. So I think we would stop here. Thank you to Vincenzo Esposito, and thanks to the audience for your interest and the nice questions.